Hello, welcome back. We formally learned about divide and conquer paradigm in the previous lecture and saw search and sorting algorithms as examples of it. Recall that divide and conquer solves a problem by dividing it into smaller subproblems and solve them recursively. These subproblems are often the same problem as the original one, but with smaller input sizes. This fits naturally using recursion, so divide and conquer often goes hand in hand with recursion. In this lecture, we will show another interesting example problem that can be solved using divide and conquer, the maximum subarray problem. This is an optimization problem. You want to invest a stock. You can only buy a fixed number of units of the stock only one time on a date, and then sell it at a later date. You buy and sell after the close of trading for the day. You have a very intelligent technique, let's say, that can highly accurately predict the stock change over a 17-day period. You need to decide on which day to buy and on which day to sell in order to maximize your profit. You may say, well, this seems easy. I will just buy at the lowest price and sell at the highest within the 17-day window. Unfortunately, you might not be able to do that. For the example here, the highest price happens on day 1 and the lowest on day 4. You cannot go back in time in order to buy the lowest first and sell at the highest. Or you could argue, I will find the lowest price and search right from it to find the highest later price. Or I find the highest price and search left to find the lowest price prior to that. This does not always work either. Here is an example. If we have the stock price change curve looks like this, this would be the lowest and this would be the highest. Apparently, we cannot buy the lowest first and sell at the highest. The right timing to buy is here, and then the right timing to sell is here. You may notice that neither of the buying and the selling dates is the lowest nor the highest. This shows that the maximum profit sometimes comes neither by buying at the lowest price nor by selling at the highest price. So the problem seems to be more challenging than we thought. What is naive brute force algorithm? We can enumerate all pairs of buying and selling days. The buying date precedes the selling date. A period of n days will have n choose 2 such pairs. We all know that n choose 2 is in theta n squared. Computing the price difference between 2 days only takes a constant time, so the overall complexity of this brute force algorithm is in theta n squared. This is polynomial time algorithm, so not bad at all, but can we do better? Also, up until this point, we should see that whenever we are given a problem, we can always try a naive brute force algorithm first, if all the possible solutions can be enumerated. It gives us a baseline to work with, and we can then try to improve from there. Although this problem can be solved directly, let's transform it into a more general problem by looking at the input in a slightly different way. We want to find a sequence of days over which the net change from the first day to the last is maximum. Instead of looking at the daily prices, let's instead consider the daily change in price. In this table, we show the daily price as well as the change of each day comparing with its preceding day. Now we want to find the non-empty contiguous subarray whose values have the largest sum. We call this contiguous subarray the maximum subarray. Now this is the maximum subarray problem. Given an array A of n integers, Can we find a subarray of A where its sum is the maximum? The naive brute force algorithm is still of the order of n squared. Can we have a better algorithm for this problem? First, we see that there are some special cases of this problem when it actually becomes less challenging. If A contains all non-negative numbers, we would simply add all the elements up. If A contains all non-positive numbers, the answer would be a set of only one item, the largest value in A. Note that we also usually speak of a maximum subarray rather than the maximum subarray, since there could be more than one subarray that has the maximum sum. The applications of the maximum subarray problem include genome analysis in bioinformatics, where we try to identify contiguous segments of gene sequence responsible for certain protein functions. In computer vision, the problem can find its application in finding highlight spots in an image. If we treat an image as a sequence of grayscale values, the highlight spots will be subsequences that have the lowest sum. The maximum subarray problem is a search problem with an input array. It seems to fit the divide and conquer paradigm, where we can divide the input array into smaller pieces and apply the same algorithm to them recursively. Let's see how this problem can be solved using divide and conquer. Given a list or an array A, we can find its middle point and split it into halves. Then we can apply the same algorithm on its two halves. This is the pseudocode for the divide and conquer algorithm. It needs a base case first. Since it's recursive, we can use any small value here, let's say 5. So if the input array has 5 or less elements, we solve it directly using brute force algorithm. Else, we follow the 3 steps of divide, conquer, and combine. We split the array A into two halves and recursively call the algorithm to solve them. How to combine the search result? From the two subarrays, we return the result with a greater sum. Are we done? Is this algorithm correct? No. There are 3 possible locations of a maximum subarray that we are looking for. When we cut an array into two halves, a maximum subarray could be in the first half or in the second half. Or it could be across the midpoint where we cut it. The algorithm we showed in the previous slide can cover the first 2 cases. But on the third one, it won't be able to report the correct answer. How can we fix this? So in the combine step, we need to add one task that finds a maximum subarray crossing the midpoint. You may wonder, does this send us back to the original problem, finding a maximum subarray? Wouldn't this be the same complexity as the original problem? Then why bother with divide and conquer? In fact, if we think really carefully, this problem is not the same as the original one. There is a restriction now. The subarray must cross the midpoint. So this maximum subarray must be comprised of 2 subarrays, where the first portion is a maximum subarray that ends with element A middle, and the second portion is another maximum subarray that starts with A middle plus 1. We are now looking for 2 maximum subarrays, of which one end is fixed. we only need to do a sequential search to find this I and this J. The complexity of finding the maximum subarray crossing the midpoint is therefore only linear. Once this is all figured out, let's add this to our divide and conquer algorithm. Now we need to do 3 subtasks. Search a maximum subarray in the first half of A, search a max subarray in the second half of A, and search a maximum subarray crossing the midpoint. Finally, we return the one with the greatest sum out of the 3. Now this algorithm is complete and correct. We can write its recurrence like this, and we see that this is the same as the merge sort algorithm. So we know immediately that the divide and conquer maximum subarray algorithm has a complexity of theta n log n. So it is indeed improved comparing with the brute force algorithm, which has a complexity of n squared. Also, as promised, I will recommend some exercise questions from the textbook on the topic we covered in each lecture. Hope you find them helpful. Okay, that'll be all for this lecture. Hope you find this problem-solving process interesting. We will have most of the future lectures like this using case studies. I hope you enjoy them. I will see you in the next video.